Hi everyone, I'm Prachi Garg and I'm here to present our work, Poet, Prompt Offset Tuning for Continual Human Action Adaptation. Human action recognition is an integral part of many applications, ranging from sports analysis, human-robot interaction to extended reality. But what is common in all these devices is that they are pre-shipped with a fixed set of hand gestures and body actions. Consider this user in a VR headset looking at a default set of hand gestures. The goal of our research is to personalize user experience. For example, this user may want to add the entire American Sign Language to interact with their virtual world. Or a developer may want to develop customized hand gestures to interact for their new game. Unfortunately, existing models cannot achieve this because once deployed, they are static. So one possible solution could be that the user asks a software provider to add this gesture for them. The software provider would then collect the data, retrain the entire model from scratch, and then redeploy this to the user's device. As you can see, this is going to be very time-consuming. So instead, what we want here is a single dynamic model that continually extends over time, and hence the need for continual human action adaptation. So let's look at the system that we have envisioned. In this, we have two user devices deployed with a default set of action classes, and each user can add any set of new classes at any time they want. So every time the user has a new set of classes to be added, our aim is to maximize the performance of the new classes and at the same time maintain the performance of the existing classes. From this system, we elicit three technical challenges that are necessary to solve this problem. The first is that as the model adapts to new classes, it must not forget or overwrite the existing classes. That is called continual learning. The second is, we want that the user should be able to easily add new classes by providing as few samples as possible. Hence, it's a few shot problem. And finally, we also want to preserve the user's privacy. So we incorporate privacy awareness in two ways. The first is by our choice of modality. Video-based human action recognition. Recent works have been trying to obfuscate human faces in videos to enhance users' privacy and security. We circumvent this entire issue by using 3D skeleton sequences as our input modality. The second way we incorporate privacy is by not storing any user data. So to put things into context, one of the most effective ways of solving continual learning is to store a subset of previous classes in a rehearsal buffer, and as the model is updated on a new class, you have to replay the rehearsal stored samples so as to avoid their forgetting. But now we said that we don't want to store any of the classes. Is there another way of implicitly learning a rehearsal buffer? Let's talk about prompt tuning. So prompt tuning has become an effective way of adapting large-scale pre-trained transformers to new tasks because they can condense task-specific knowledge into a set of learnable prompts that are concatenated to this input while keeping the backbone frozen. Now, in a continual learning context, we have a sequence of tasks that are coming in. So we can train a set of task-specific prompts for each of these tasks and store them in a pool of prompts. So over time, task-specific knowledge is getting accumulated in this pool of prompts. And as you can see, this is a very natural alternative to storing explicit samples which would violate a user's privacy. So keeping this in mind, I propose our architecture. The input to our model is a 3D skeleton sequence of T temporal frames, and each frame has J joints of the human body or hand skeleton. And this is passed through an input layer to get an input feature embedding, and subsequently passed through a feature extractor and a classifier to get the action label. Now, the feature extractor in such works is typically a graph neural network. So instead of concatenating prompts to a transformer, we propose to prompt offset tune a graph neural network by adding these learnable prompt vectors to the input feature embedding. And as the user adds new classes, we expand the classifier and update the classifier and the prompts. Now you must be wondering, how are these prompts defined and where do they come from? So we have a prompt selection mechanism which gives us these prompts for each input instance. In our prompt selection mechanism, we have a pool of prompts, which is like a memory pool. And for each input instance, we want to select the relevant set of prompts from this pool. So we construct a set of key parameters corresponding to the prompts, and we get an input condition query, with which we compute a cosine similarity to find the relevant prompts. So the query key cosine similarity is then sorted. So we sort the cosine similarity and select the top t indices from this. And the significance of this is we want to design a prompt selection mechanism where this prompt selection is temporally consistent with respect to the input. So the input has t temporal frames, and if we select them in an ordered way, we can capture the temporal order dynamics of the input sequence. Once we have this sequence, we read the prompt pool in this ordered sequence and get the final set of prompts, which are finally added to our input feature embedding. And we find that this ordered selection and addition helps us learn the new classes much better. So another issue that we faced here was that for 3D skeleton sequences, we could not find large pre-trained transformer models at the time. And so our query function is actually pre-trained only on the base set of classes. It has never seen the new classes. So as the model sees new classes from the user, the query function must be updated on the new classes so that it can distinguish instances of the old and the new classes. So unlike existing works, we propose a coupled optimization wherein the cross entropy loss for the new classes is used to update the classifier, the selected prompts, keys, as well as a query adapter layer in the query function. Now, coming to related works, there are existing works in few-shot continual learning, especially for the image classification literature. And there are also works in data-free continual learning. But POET is the first attempt which covers all the aspects of this problem. So we contribute 2 new benchmarks to simulate and evaluate our problem setting. The first is on continual activity recognition. We use the NTU RGB plus T dataset for 3D skeleton activity recognition. And the second is on continual hand gesture recognition, where we have used the Shrek 2017 dataset. Coming to our results, for the activity recognition benchmark, we prompt tune a graph convolution network, CTR GCN to be specific. And as you can see, in the base session, we have 40 daily action classes, and we use full supervision to train the model in the base session. And in the incremental sessions, we add 5 new classes over 4 user sessions. So the user is adding 5 new classes in every session. And by the end of the last session, we have 60 classes. And in each of these classes, we use only 5 training samples to update the model. So as you can see, we compare POET with feature extraction, which is simply POET without prompts. So that has a frozen feature extractor and a classifier which is expanding. So this shows the significance of prompts as isolated by themselves. And as you can see, we have a prompt tuning only solution for continual learning. We don't use any knowledge distillation or other techniques for this. So coming to the second benchmark, here we prompt tune a graph transformer network, that is GGSTA. And here we have 8 classes in the base session, and we add 2 new classes incrementally, again using 5 samples per class. And here as well, we observe a significant improvement. So to recap, we have proposed a practical and challenging problem of continual human action adaptation and propose a prompt offset tuning solution which acts like a plug and play into most architectures. We show results by prompt tuning a GCN and a graph transformer. And we have 2 new benchmarks on activities and gestures. We have a lot of interesting details about the method and insights into the experiments. So please visit us at poster number 211. Thank you.